All right, for posterity, this is the Exam 1 review for Math 234 Multivariable Calculus in the spring semester of 2024. I'm your host, Steve Dragoo, and let's get this thing started. If you want to look for a written record of this review, of the notes that I'm about to be making, you can find that on D2L. If you navigate over to my completed course notes, it should take you to a OneNote document that looks very similar to this one. Just click the exam review tab on the left and the exam 1 review will be there. Chances are by the time you're watching this video, that's the only exam review that's available. But if you happen to be watching this later on in the semester, I'll have exam reviews here for each of the 4 exams we take, all 3 midterms, and then also a final exam. Although I think I'm going to call it a post-exam 3 review, because I'll just be reviewing the stuff that's after exam 3. That's not super relevant to what we're here for today, though. So let me go ahead and get started with that. Just to make sure that we don't run into any problems. I mean, my video is never in the way when I record these things. I'll leave my video on. That's fine. Be a little floating head in the corner. All right. Let's start this review. So my plan is to go over a few problems out of the web work, stuff that I think that is going to be fairly relevant to the exam that you take on Thursday. That's this Thursday, February 1st, from 7 to 9 p.m. on D2L. And again, these are the problems that I think are going to be relevant to that, or at least some problems that I think are relevant to that exam. So again, I digress. Let me just start doing math. Okay, the first one I want to do, 3D from the very first homework set. And I'll try to keep these problems in order. Finding the equation of a sphere that's in standard form, centered at -1, -4, 4, and with a radius of 5. So just to remind us of what that thing looks like, the equation of a sphere looks very similar to the equation of a circle, just with a z term added in. So we want x minus x1 squared plus y minus y1 squared plus z minus z1 squared. And all that is equal to r squared. Where we just start color coding some things here. X1, Y1, and Z1, or maybe X naught, Y naught, and Z naught. All of those are a point. So all of those values are numbers, whereas X, Y, and Z, without the subscript, each of those are going to be the variables, X, Y, and Z. So all we've got to do is plug in numbers for X1, Y1, and Z1, and then also a value for R. So specifically in this equation for the sphere, it is the center that's represented by X1, Y1, Z1. And the question was kind enough to just tell us what our center is, -1, -4, 4. So all we've got to do is plug those numbers in. This becomes x plus 1 squared plus y plus 4 squared plus z minus 4. That thing squared, and it's equal to 5 squared. As we're told, our radius is 5. Cool, and that's all we had to do for that problem. One thing that might be worth reviewing is, so this was one direction that the problem could go. You're provided a center and a radius and asked to come up with an equation. Another way this problem could go would be given some equation, find its radius and its center. So if I continue just working with this problem real quick, just to extend it beyond the web work. If I were to FOIL this whole thing out, And I guess that means create a little bit more space here. FOIL the whole thing out. I'm going to get x squared plus 2x. Let's go. Plus 2x plus 1. Slide a little over. Plus y squared plus 8y plus 16 plus z squared minus 8z plus 16. All that's equal to 25. And then I could gather up all my terms over on one side. Or at least put all my constant numbers over on one side. So let's see, that'll be 25 minus 32, which would be, what is that? -7 minus 1 is -8. So -8 will end up over there. I'll have x squared plus 2x plus y squared plus 8y plus z squared minus 8z. All right, so if we were to go with this problem in the other direction, starting from an equation to try and figure out the center and the radius, we would just work our steps backwards. Where we'd need to complete the square on each of the three variables. So complete the square for x, for y, and for z in order to find our center. And then all of the leftover constant terms added up, we get the square root of that to find the radius. So I think that, if we're going to ask a question about a sphere and its equation, we could ask the question from either direction, either starting with a center and a radius, find an equation, or start from an equation and figure out the center and radius. Cool. All right, so let's move on. All right, some stuff from the dot products. Conceptually, we want to decompose A into a pair of vectors. That the pair of vectors is going to be C and D, one of which is parallel to B and the other is orthogonal to B, some extra vector that we want to project it onto. So from a conceptual perspective, I drew the picture out ahead of time just so we know what we're looking at. But I've got my blue vector A, and I want to project A onto the gray vector B. So B, I only care about its direction. I don't care about the magnitude of B. I just care the direction it's going in, because I want to decompose A into the other two vectors I drew on here, the yellow vector and the magenta vector. One of those is parallel to B and the other is orthogonal to B. And the idea here is that if I take my two new vectors, C and D, and add them together, I get my original vector A. Since if I trace the path along C and then up D, I get to the same point if I would have just traced my path along A. So this gives us the starting concept that my vector A is equal to C plus D. So that's when I say I want to decompose A into a pair of other vectors. I want to rewrite this as two vectors that still add up to A. And I know that they add together because, again, they reach the same point by the time they're done. So from a concept perspective, that's what we're doing. From a more math-oriented focus, this means we're going to be working with a projection. So we know that we can project one vector onto another. And the way to do that is to just take the dot product of the two vectors that I'm interested in. divide away the magnitude of the vector that I am not interested in its magnitude. So again, I don't care about the magnitude of B, I only care about its direction. So when I take the dot product, I want to divide out the magnitude of the vector I'm uninterested in, and then I want to multiply that number into the unit vector in the direction I care about. So multiply it in the unit vector in B's direction. So at every step of the path, at every step along my process, I want to divide away the magnitude of the vector that I don't care so much about. So I'm dividing away B's magnitude at every step that I can, or at every step that I need to. Yeah, probably better to say at every step I need to, and every step I can. Okay. But man, I keep just talking about stuff instead of doing things. Let me actually do something. So this projection, I need a dot product of a blue vector, which was -3, 5, -5. I should have that on screen while I write this down. There we go. Up and oh, it's in the upper left. -3, 5, -5. And I want its dot product with the gray vector B, which is 1, 10, -2. Burp, burp. Divide away the square roots of 1 squared plus 10 squared plus 2 squared. 1 squared plus 10 squared plus, let's just call that -2 squared. Usually I'd take the shortcut of just saying that that is 2 squared, because I know that negatives are going to get squared away. But for the sake of completeness, I'll be sure to write in the actual number that it's coming from. And then I want to take the dot product of that with the unit vector in B's direction, which would be the vector 1, 10, -2, divided by the square root of the same thing. But I'm just going to rewrite that to be a little bit easier. Instead of multiplying by 2 identical square roots, I'll just say that it's the original square root squared. And that way I'm just multiplying into that B vector. So I can collect all of my coefficient in just one numerical term and say that it's some coefficient times B. Since if I look back at this vector C that I'm after, the yellow one, over in the lower left part of the screen, C is just some scalar multiple of B. The yellow vector is a scalar multiple of the gray vector. And here I've got it written out as exactly that. But let's go back and add some color to this example. That was the blue vector. This is the gray vector. This one also is our gray vector. And all of these numbers down here come from the magnitude of the gray vector. Yep, I missed a spot. Okay, so that's the math that we need to be plugging in somewhere. So now we just have to go and do that. So if we multiply stuff across the top, we'll take the minute to actually multiply this dot product all the way out. -3 times 1 is -3. 5 times 10 is 50. And -5 times -2 becomes +10. Divided by, down below, I have the square root squared, so those two parts will annihilate with one another. Although, no, we don't even need to worry about an absolute value, because we already know that our inside is positive. 1 squared is 1, plus 100, plus 4. And then all of that is being multiplied into the vector 1, 10, -2. And finally, I'll just clean up that coefficient 50 plus 10 minus 3 is 57. Divided by 1 plus 100 plus 4, it's 105. And again, I still have my vector 110, negative 2. And all of this is our C vector. That's the part that is parallel to B. That's our projection of A onto B. So past that, we also want to get the orthogonal vector that accompanies it. And the easiest way to get that, to my mind, is to just rearrange that equation I had above. If A is the sum of C and D, that means that D is the difference between A and C. And I already know what all of these are. A is the vector negative 3, 5, negative 5. That was given to us. Minus C, which we just found, was 57 over 105 times 1, 10, negative 2. If we throw some color back in here to see where all that's coming from, that blue part was our original vector A. The gray part was our original projecting onto vector B. And then it's this component out in front, the bit in yellow, that scales the B vector to become C. So D is just a sum of the A vector and some component of the B vector. Cool. And this is where I would leave things personally. Trying to multiply 57 over 105 into that vector is just going to make each individual number a lot messier. So I would leave it right here. And then maybe calculating one of those positions if I need to for a D2L answer. Okay. Let's take a look at another good one. Suppose we know the magnitude of A, the magnitude of B, and the angle in between A and B is pi over 3. Figure out what the magnitude of the cross product is equal to. So there in gray, I wrote down another formula that might be of interest to us. That is the definition of the dot product. So the dot product is A dot B is equal to the magnitude of the two vectors multiplied together times the cosine of the angle that's in between them. But if I want the magnitude of the cross product, it's a very similar looking formula. Magnitude of the two vectors multiplied together. And then instead of multiplying by the cosine of theta, I'm going to multiply by the sine of theta. So the dot product ends up being related to the cosine of the angle in between the two vectors, whereas the cross product is more related to the sine of the angle in between the two vectors. But with that definition, all we really have to do is just plug some stuff in. The magnitude of A is 4, the magnitude of B is 2, and the sine of pi over 3, let me just write that in. The sine of pi over 3 goes there. So then this is 8 times the square root of 3 over 2, if we remember stuff from our unit circle. Sine of pi over 3 is root 3 over 2. Or if you've taken trigonometry at Michigan State, you've probably heard me teach you that before. So hopefully you haven't forgotten your unit circle. I did say it was going to come back, and here it is. But I digress. 8 times the square root of 3 over 2 is 4 square root 3. And we're done. With that problem, though, not the whole review. I'm sure if you look at the time remaining in this video, you'll see there's quite a lot left. I'm so good at staying on task. Okay, let's do another problem out of the cross product section. So what do we have here? We want to find the area of triangle ABC where A, B, and C are each a point somewhere in space. So if we go to look at the triangle we're talking about, it's this one that I've sketched over to the right. I've got my 3 points, A, B, and C. All together, they make a triangle. But in addition to that triangle, I'm drawing in the implied parallelogram that goes along with that triangle. Because the thing that we calculated previously, the magnitude of the cross product, which is just the magnitude of our two vectors times the sine of the angle between them, that does have a geometric interpretation. And the geometric interpretation of this cross product magnitude is the area of the parallelogram that's implied by the two vectors. So take any two vectors, it generates a parallelogram, and the magnitude of the cross product will give us the area of that parallelogram, which means if we're after the area of just the triangle, it should be half of the area of that parallelogram. So it's right here, area is equal to 1/2 times the cross product of, let's write it U cross V for right now, because we haven't defined what our vectors are just yet. Which means we should probably do that right now. Our two vectors, at least with the way that I've drawn the diagram, two vectors I'm going to care about are A, B, so the vector that gets me from point A to point B, and A, C. The vector that gets me from point A to point C. So if I want to go figure out what those are, this is just the final point minus the initial point. So I want B minus A. So this becomes -6 minus -3. For the X component, I'm looking at 3 minus 1 for the Y component, and -2 minus -2 for the Z component. Add up each of those, and hopefully we get -3 to 0. At least if my math is right, that's what we get. I'm sure that if I mess that up, someone will let me know in the comments. Cool. So that's the first vector I got, -3, 2, 0. I should do the same thing to get a C. This is -5 minus -3, 1 minus 1, and -2 minus -2. Which, adding all of that up, I got -2, 0, 0. So those are my two cross products. And I'm going to want to get, or excuse me, those are my two vectors. I am now going to want to get the cross product of those two vectors. So let's do that. AB cross AC. AB cross AC. And it'll look something like this. I, J, and K. I'm going to write in across the top row. I'll write my first vector, AB, across the middle row, -3, 2, 0. Write my second vector on the bottom row, -2, 0, 0. And calculate a cross product of that thing. Fortunately, this is a pretty nice cross product to calculate, since I've got one column that's all zeros. Since the K column is all zeros, that means that the Z component is the only component that will be non-zero. So the X component is 0. Both of the bits in my cross get multiplied by 0. The Y component is also 0. Both bits get multiplied by 0. And finally, my Z component, -3 times 0 minus -2 negative 2 times 2. And all together, I get the vector 0, 0, 4. So for my last step, just put it all together. The area of this triangle should be 1/2 times the magnitude of AB cross AC, which looks like 1/2 times the square root of 0 squared plus 0 squared plus 4 squared. If you wanted to jump straight to the magnitude, that vector is 4. I think that's completely fine. But for the sake of being complete about my work, I wrote it all in. So 1/2 times 4 is 2. So that triangle has an area of 2. All right, let's take a look at our next one. Start off with an easy question about planes before we dive into a more complex one. So we want to find a non-zero normal vector to the plane, the one that's given there, z minus 5 times x minus 3 is equal to negative 4 times 4 minus y. So what I'll do is I'll just multiply everything out, group it all on one side, and come up with a normal vector. So if I multiply stuff through, this equation could be rewritten as z minus 5x plus 15 is equal to negative 16 plus 4y. And then now I'm just going to group everything on one side of the equal sign. So I'll bring everything over to the left side and put them in order. Negative 5x minus 4y plus z plus 31 is equal to 0. Here we have it. And then I just need to pick out a normal vector, which means to get that normal vector without working too hard, I should just take the coefficients on each of x, y, and z and say that that's my normal vector. So n, usually use n for normal vector because n for normal. That thing is the vector. Stop right. Just try and draw that in without being too ugly. Negative 5, negative 4, positive 1. So that is a choice for a normal vector. I haven't done anything fancy like finding a unit normal vector or anything. I just found any non-zero normal vector, and this one will do. So if you have any scalar multiple of this vector, that would also be a valid answer. The most common scalar vector, in addition to this one, the most common scalar multiple of this vector, in addition to this one, would be this thing times -1. So like 5, 4, -1, also a normal vector. So if you just grouped things on the right side of the equal sign instead of the left, you would have gotten 5, 4, -1. Oh, so again, either one of those will be completely fine. You should be able to give any answer unless we ask for a very specific kind of vector on the exam. Like maybe one that's oriented upward, meaning that it has a positive z component. Something like that. But I don't think we're diving into that on this first exam. So no need to worry about that yet, but maybe store it away for later. We will eventually be going to stuff like that. But all right, this next one, I also sketched out the problem ahead of time. Save us just a little bit of time here. We want to find the distance between the plane given by that first equation and the line given by that second parametric equation. So sketched out what those two things look like. And if we're being given a problem like this, where it says find the distance between the plane and the line, I suppose we should probably check to make sure that the line and the plane are indeed parallel to each other. Because if they aren't parallel, then that means that somewhere in space, this line is going to have to intersect the plane, meaning that the distance between them is 0. So it only really makes sense to ask this question, distance between a plane and a line, if there's a consistent distance between the line and the plane, meaning that they never intersect. So if we wanted to do that check real quick, check to see that the line and the plane are parallel to each other, we would just need to check that the parallel vector for the line is orthogonal to the normal vector for the plane. Should you check that on the exams is a question that I see in my psychic brain and also in my Zoom chat right now. So should you check it on the exam? I think that if you have time, you should come back and show this step at the end. But since the exam is timed and you're going to have plenty that you're going to be worrying about outside of this check, save it for later. Because if we ask, I mean, a test-taking strategy that I might provide is that if we ask that question, find the distance between the plane and the line, it's because they don't intersect each other. But yeah, this is sort of like for best practice, we should be checking this. So where's the spot that I could do that? I'm going to take the normal vector, 1, 3, 2. I'm going to take its dot product with the parallel vector, which is 2, 2, -4. Multiply that stuff together to get 2 plus 6 minus 8. And that is indeed 0. So anytime we take the dot product of two vectors and find that we get 0 after we take the dot product of, again, two non-zero vectors. So really just, yeah, any vector that's not the 0 vector, take the dot product of two of those. If their dot product is 0, that means there's a right angle between the two vectors. It means they're orthogonal to one another. So by definition, for the dot product, the only way the dot product is 0 is if either the magnitude of A is 0, the magnitude of B is 0, or the cosine of theta is 0. And since we already made the assumption that neither A nor B have a magnitude of 0, that leaves only cosine theta being 0, and cosine theta is 0 when theta is 90 degrees. But again, I digress. Let's take it back to the meat of this problem. Figure out what our plan is here. So I should do a couple of things. First, I'm going to pick some point in the plane. Doesn't matter what point. Any point will do. And I'm going to call that point P. Right? Like, why not? It can be P. P for point in a plane. And then I need another point. This time a point that's on the line. And doesn't matter where on the line it is. It can be anywhere. Since I called the first point P, I'll call the next one Q, just because they're right next to each other in the alphabet. And I want to kind of get the distance between those 2 points. Right? The distance between those 2 points would tell me something about the distance between the line and the plane, but not quite everything. So if I pull out my ruler here, draw the vector that connects these 2 points. Maybe it's a 49-degree angle instead. I can just move my point so that it matches a little bit more nicely. Slide to the right. Yeah. So this is my vector PQ. what I want to do in order to find the distance between these two planes is project this vector that I just drew onto the normal vector. So I'll put this thing at a 90-degree angle, come back over to right here, draw in the extension of that normal vector, and say that if I just look at this bit right here, this yellow bit here, maybe give it a name, maybe call it C, so that it reminds us of something we did earlier. That yellow vector is just a projection of PQ onto the normal vector, just like what we did in the second problem out of this review. So if I'm after that that distance, I want to project PQ onto the normal vector and go from there. And since all I want is the magnitude of that vector, I don't even need to take the dot product into the unit normal. I just need to get the component of C. So start writing some of this stuff down because we need a few things here. Chiefly, I'm after. Okay, come back. What is it I'm after? I need the points P and Q. They are somewhat arbitrary, so I can pick them from just about anywhere. But Q at least has a pretty obvious choice. I'm going to say that Q is the point -1, -2, -1, where I'm pulling that from the equation of the line. Right, because the equation of the line has some initial point baked into its equation. If I just pull that out, I can use that for Q. So this comes from t = 0. I also need a point P. So something that fits in with the equation up there. And I'm going to argue that the easiest point to use is -23, 0, 0. And I got this point by just taking y = 0 and z = 0. So since a plane is just an infinite collection of points, if I look at, where do I go? If I look at the equation of my plane, I've got 3 variables, but only one equation. So I've got an overdetermined system, overdetermined by 2 variables. So I get 2 free choices. And I think the easiest 2 are just to claim 2 of those numbers are 0 and figure out what the third one is. So I can verify that that point is in the plane by just plugging in my numbers for x, y, and z. -23 for x and 0 for the other 2. All right, so I've got my points. Now I need my vector PQ. So PQ. And it's a vector. Specifically, it's the blue one. If I write out what that vector is, what do we have? I've written it PQ, so final minus initial. It's going to be -1 minus initial, which is -23. Then for the y coordinate, Q is -2 minus P, so -0. And then -1 minus 0 again. That gets me to the vector 22, -2, -1. right? And then that math's not too bad. I just had to add 23 to the x coordinate of Q. All right, so finally, I want to get the magnitude of C because I know that's going to be my distance here. So my magnitude of C is something. It is the component of the vector PQ that goes in the direction of the normal vector n. So if I just need the hey, come back. Wanted that in gray. If I just need the component of that vector, I need their dot product. 22, -2, -1, dotted with the normal vector, which I wrote down earlier. But let me go grab it again. That normal vector, n, from my plane equation should have been 1, 3, 2. So, yep, and I'm using that to get that equation of the plane to get the normal vector. My normal vector was 1, 3, 2. And to get the component, I just need to divide away the magnitude of that normal vector. 1 squared, let's try and write that a little bit straight. 1 squared plus 3 squared plus 2 squared. Highlight where all that stuff's coming from. That's our blue vector. This one's our gray vector. And calculate a number here. This is across the top. 22 minus 6 minus 2 divided by the square root of 1 plus 9 plus 4. 1 and 9 is 10, plus 4 is 14. I've got some space. I can write that at 1 plus 9 plus 4. So this is equal to 14 divided by the square root of 14. And that's an easy enough simplification to square root 14. Cool. So another question that I can see someone asking because I'm a psychic and also because I can look at my Zoom chat. Why do we use the component instead of the projection? Why do we use comp instead of proj? If I were to examine the difference between those two things, the scalar projection, which we call the component, and the vector projection, which is the thing that we just call projection, because they're both very related to the two pieces, but the key difference is in the way that I labeled the two styles of projection. One is a scalar projection, and the other is a vector projection. Okay, sorry about that. Hopefully I muted my mic in time. Okay, so that scalar projection then, which is the component, is just going to give us the magnitude of the vector. Scalar being just a number and magnitude also being just a number, as opposed to the vector projection, which gives us a vector answer. We are looking for the distance between a line and a plane, and a distance is a scalar value. Distance is just a number. So that's the bit that we want. We want only the scalar projection, the magnitude of the vector projection. Which is why we just calculated the component. Let me go grab something else from right here. If I was smart, I would have just stashed it off to the right side of the screen. Oh no. Looks like I wasn't that smart though. Okay. Then, instead of all of that, let me cheat another fanciful way. And just copy something from another part of the notes that I want to bring in, because there was a second way we could have done this problem. One that I think loses some of the conceptual explanation, but is faster. So I'm going to just copy that from another spot that I have in the notes. Try and make it look like I'm at least a little bit prepared for this review that I'm doing. Yeah, this is the section I wanted to be at. Paste me in right there. And now, come on, give me my scroll bar, you big meanie. Like, can I seriously not get my scroll bar right here? Okay, fine, fine, fine. Now it lets me do it. Okay. If I put it right there, hey, look, my handwriting is so similar to the last time I did this problem. It's like I've been practicing. Well, don't give me that. Back here. Okay. There we go. Now that the stuff has pasted in and even to the right spot, here's the other method we could have used to calculate the same thing. This time, using a slightly different formula to get the distance between a point and a plane. Where the numerator, instead of being the, instead of being the, back that up again. Replacing the numerator, which was the dot product of PQ with the normal vector, I could instead say it is just the equation of the plane with the point on the line plugged in. And then the absolute value of that gives us our answer. So this formula right here, D equals this whole thing, is a formula that you could just go to and come up with a value that's maybe a bit faster than the method that I just detailed. However, the part that I mentioned moments ago was that maybe you lose some of the conceptual understanding if you just plug into the formula, which is why I spent all the time going over the explanation I did. So this is just a snippet that's out of my notes from somewhere, and this would have been in the lines and planes section, where it's still the same process. The distance is just the scalar component of v in the direction of n. Here I've labeled what was PQ as the vector v. But then I'm going to claim that v dot n, the numerator of that scalar component, is the, again, equation of the plane with the point on the line plugged in. You have to be careful with this equation, though, because I see it go wrong quite frequently. It's important that you write the equation of the line as, or the equation of the plane, excuse me, write the equation of the plane as a bunch of stuff added together equals 0, right? So you've got to have 0 on the right side of the equal sign in order for that equation to work. And that's an easy to forget step that I see cost people points all the time, which is why I'm being a little bit extra about be careful if you use this formula, because I see a lot of equations where d, the constant term, is left on the right side of the equal sign, and then it gets the wrong sign value, or it gets the wrong plus or minus sign when it gets plugged into the distance formula. So just have to be a little careful with that. but this thing can still work. And the nice thing about it is that if we just look at v dot n, which is pq dot n abc times x, or abc dot with x1, y1, c1 is just the normal vector dotted with the point. And then d is just what we'd get if we plug in any point on the plane into the plane equation. Which is why that thing works. The explanation, like I said, isn't as coherent as the explanation that I did previously, but I do think that it can save some time if you'd prefer to use that equation. Here's the math of plugging all that stuff in. Looks very similar. We still get the same 14 over square root 14, which ultimately is just the square root of 14. Okay, cool. So that explanation went on for a while, but hopefully you found it interesting. If not, hopefully you just decided to skip ahead to right here for anyone watching the video. For those of you who weren't, sorry. Okay. Everyone's favorite, identifying quadratic surfaces based on their equations. So, what's there to say about this section? Probably kind of a lot. So let me start saying kind of a lot. When it comes to identifying these surfaces based on their equations, I think the number one most helpful hint I can give is to ignore all of the numbers. They do not help you. So like this z squared over 4, I'm just going to pretend the over 4 doesn't exist. Maybe I'll cross it out so it's still a little legible. Get rid of that over 4 there. I'm going to get rid of that over 4 there. All of these are over 4, which isn't all that common, but either way, if there are extra numbers in the problem, I'm simply going to ignore them. The only things I'm going to care about are the coefficients that go on any of my x, y, or z values, and a constant term if I have one. But every single number, at least in my head, when I'm doing these problems, is 1, -1, or 0. And if it's not one of those numbers, I ignore it. So z squared over 4, I'm just going to pretend that's z squared. And it's going to make identifying these surfaces quite a bit easier, I think, anyway, because I can then take that first equation, which is x squared plus z squared over 4 equals 1 plus y squared, and I'm going to rewrite it to be something different. I'm going to rewrite it so that it is x squared plus z squared minus y squared equals 1. Because I think that equation is just easier to identify than the one before it. And the numbers won't actually change what type of shape it is. It'll only change its scale. So writing it into this form, what do I want to do? I want to start trying to classify that thing. And over here to the right, I've written in the way that I tend to think about how to classify all of these shapes. I split it up into 4 sections, 2 of which are very easy to identify, one of which is easy enough to work with, and the other one is always the one that gives everybody trouble, the one at the bottom. So let's get to that one last. Starting with cylinders, they're the easiest to identify. Anytime we have only 2 variables in our equation, it's a cylinder. If we have some 3-dimensional shape that is completely independent of one of our 3 variables, it's a cylinder. Doesn't matter what the base is. Now, traditionally, if you hear the word cylinder, you're thinking of what we in super hardcore Calc 3 math would call a circular cylinder, because it's a cylinder with a circular base. And that's, I mean, if you just think of a cylinder, you're thinking of something like a pop can. Where's my camera? Like a pop can. It's a strawberries and cream Dr. Pepper. That's a cylinder. But when it comes to the super fancy definition that we're going to start using in Calc 3, because we don't want to make things easy, we're going to claim that a cylinder can have any kind of base. The only thing that's important is that there's one variable, there's one direction that's independent in the equation. So in the equation I wrote up at the top, x squared plus y squared equals 1. Doesn't matter what z is, the shape always looks like a circle, because that one happens to be a circular base cylinder, but it could be anything. So again, a cylinder in the context of this super fun Calc 3 definition that we have means that there are only two variables in the equation. So it's defining some two-dimensional shape and then just extending it straight up one of the axes. Then an ellipsoid is basically a sphere. And as long as I ignore all the numbers, an ellipsoid is a sphere, because it's the numbers that transform a sphere and make it an ellipsoid instead. But it's just I group up all of my x, y, and z square terms on one side. I'm adding all of them, which is important, and they're equal to the square of the radius on the other side. So I think spheres are pretty easy to identify, and by extension, ellipsoids also end up being pretty easy. Then the paraboloids, also fairly easy to identify when something is a parabolic shape. And then we just have two choices for what kind of paraboloid we want. So step one, identifying a paraboloid, I'm going to have a linear term mixed in with some square terms. And that is the quintessential parabolic shape. You think back to the standard parabola, y equals x squared. I have a linear term, y equals a square term, x squared. So paraboloids work the same way. There's one linear term mixed in with a pair of square terms. And we don't ever need to consider a constant term when looking at paraboloids, because we could always choose to recenter the thing so that our vertex is at the origin. Because we're claiming that all of these shapes are being untransformed or transformed in a way that is nice for us to look at. So we just need to decide between an elliptic versus a hyperbolic paraboloid. And an elliptic paraboloid is one where the equation reminds us of a circle. If I put everything on one side, I get x squared plus y squared, or maybe negative x squared minus y squared. Either way, my two square terms have the same sign in an elliptical paraboloid, because again, the equation should remind us of an ellipse or a circle. And in a hyperbolic paraboloid, the two square terms will have opposite signs. Remind us more of a hyperbola, some sort of hyperbolic shape, which is what happens if the two square terms have opposite signs. And finally, the various hyperboloids that we could have. And I've organized them in the way that I think makes the most sense to me. So I'm also going to think of an elliptic cone as being a special hyperboloid. So I'm going to group it so that all of my square terms are on one side. I'm going to put my constant term on the other side. So x, y, and z all on one side. Number goes to the other side. And then I'm also going to organize it so that I have two positive terms and one negative term. So two of my variables are positive, the other's negative. If you have the opposite of that, one positive, two negative, just multiply everything by -1, and it'll transform it into this. And then I'm going to organize it into that whole thing equals a positive number, that whole thing equals 0, or that whole thing equals a negative number. Because that then helps me remember what's going on near the origin. If the whole thing's equal to 0, then at the origin, the thing just intersects the origin, because that all comes together at one point. And then that point, again, it's the origin, but that makes it a cone if it comes together at that point, because cones have that nice sharp point right at the end. And in Calc 3, our cones are going to be both the top and the bottom of the cone, make it look sort of like an hourglass. But I digress. So that's a cone. And then I can either increase that number by 0, or that number near 0. You can either increase that number or decrease that number to create hyperboloids of either 1 or 2 sheets. If I make that number positive, so near the origin, I've got a positive value, then I'm looking at a circle intersection near that origin, near that center point. And if I have everything comes together at a circle, then I have my 2 shapes of my hourglass smashed together to make a circle, and end up with a hyperboloid of 1 sheet because it's all connected. Versus if I imagine taking that hourglass shape and pulling them apart from one another, which is what's going to create my hyperboloid of 2 sheets, that means I'm going to have a negative value near the origin. I've got something like x squared plus y squared equals a negative number, which is like an anti-circle or an imaginary circle, because the radius ends up being some negative number. And it's that negative value that separates the 2 sheets of the hyperboloid. And so that's how I think about all this hyperboloid stuff. Maybe you find that useful. Maybe you thought it was just me being long-winded for no reason. Sorry if it's the latter. But this is a way that I think is helpful for organizing my thoughts to put it all together. So if I do all of that and bring it back to the very first problem that we were looking at, I know it's been a minute, but I reorganized this thing to x squared plus z squared minus y squared equals 1. I've got 1 negative square term, so I know it's a hyperboloid of some kind, and it's equal to a positive number, so it's only 1 sheet. This thing is a hyperboloid of 1 sheet. All right, all that to get just the first answer. I promise the rest will go faster. The next one down, I think we can see if I just added that z squared to the other side, all 3 variables would be positive, meaning that's an ellipsoid. The next one down, I've got x squared equals y squared plus z squared. That one looks like a cone. Right, there's no constant term, but all my terms are square. So that thing's a cone. Down 1 more, x squared minus z squared, x squared minus y squared minus z squared equals 1. I want to just like star this thing right here and rewrite it down below, because I'll reorganize that into negative x squared plus y squared plus z squared equals -1. So I get that -1 that shows up on the other side. And that makes it a hyperboloid of 2 sheets. So this guy's a hyperboloid, but this time it's 2 sheets. Next one down, that's just the unit sphere, but we're calling those ellipsoids for now, because a sphere is all spheres are ellipsoids, but not all ellipsoids are spheres. Similar to that square rectangle problem. I just forgot how to spell ellipsoid for a second. There we go, spelled just like it sounds. And this last one, x squared plus z squared equals y squared. That's another cone. All square terms with no constant term. So I also included the textbook page that talks about how to classify all of these shapes, but the textbook page ends up being a little more complicated than it needed to be. So I tried to simplify it a bit in my own words to hopefully make it a little bit nicer looking. And then just in case you thought I haven't been long-winded enough on this problem, I've got one more classification that might help ring things together. So my paraboloids, my hyperboloids, and my cone grouped into three different sections. The paraboloids, that'll happen, like, again, I think the paraboloids are pretty straightforward. It's elliptic if the square terms have the same sign. It's hyperbolic if they have opposite signs. It's the hyperboloids that are always the fun ones. And by fun, I mean fun in the charming sense, because suffering is part of our charm. That didn't work. Forget I said that. Another way to classify those hyperboloids between one or two sheets. If you just group up all of your terms in a hyperboloid so that every term is positive, then just look on the side of the equation that has the constant term. If there's one variable with the constant term, that's one sheet. And if there's two variables with the constant term, that's two sheets. That also works. Use some of the conceptual idea of what's happening if you do it that way, but it does get you to an answer very quickly. Just make everything positive, count the terms next to the constant term. And then it's a cone if there's all square terms and no constant term. Okay, let's move on to some stuff that's past quadratic surfaces. Oh, wow, it's 9 o'clock already. Okay, some vector functions. Moving into chapter 13. What do we have going on here? Given r prime is some vector and r of 1 is some point, figure out what the original function should have been. So find r of t. So this is finally some calculus. All we want to do is just integrate each of these pieces. So I'm going to claim that r of t is equal to the integral of each part of r prime. So I'm going to integrate 10t plus 4 dt, where 10t plus 4 is that bit. Then I'm going to integrate 5, and then I'm going to integrate 12 square root t. So the next part should be the integral of 5 dt. And the next part over, that next part over, should be the integral of 12 square root t dt. And hopefully we haven't forgotten all of our Calc 1, because it's not so bad. This thing, oh no, hang on. My pen has decided to disconnect. Love that for me. So hang on 1 second. I'm going to go try to fix that. All right. Hopefully it's still working now that I've unpaused. Brilliant. Okay. So integrate each of those pieces. Should give me 5t squared plus 4t. And it should give me 5t. And it should give me the integral of 12 root t, which is going to be 8t to the 3 halves. 12 times 2/3 is 8. And if you were really a fan of all the various rules in Calc 1, you'll probably notice I'm forgetting something when I calculated all of those integrals, and that's that each of those should have a plus c on them, plus some constant term. But I thought it was easier to just write it as one constant vector that gets added in. Make life a little easier for me if I can group all of my c's together. Because this is the point, this is the part where I can use the point provided to me, r of 1, to figure out what each of my c values ought to be. So r of 1 is equal to my point 9, 10, 12, where 9 was the x part, 10 was the y part, 12 was the z part. And I also know that it should be equal to whatever I get when I plug 1 into the equation that I just got. So 5 plus 4 goes right there. 5 for the middle part, 8 for the z part, plus the vector c, which I'm now going to call c1, c2, c3, PO. I don't make that joke often enough. That's probably because it doesn't come up that frequently. Okay, so let's figure out what c's got to be. For the x component, I know it's got to be equal to 9, and I already have 9 from the purple part, so that one, c value is going to be 0. Then I know it should be equal to 10. I've already got 5 from the yellow part, so I need 5 for the c part. And then for the z component, I know it should be equal to 12. I've already got 8 from the magenta part, so 4 needs to get added in. So 0, 5, 4, that's my c vector. So now I just have to write out my whole equation. R of t with all the numbers plugged in is 5t squared plus 4t plus 0. I'll add it in just for completeness' sake. Y component is 5t plus 5. And my z component, 8t to the 3 halves plus 4. And there we have it, a vector function. All right, and then the other favorite topic that pretty much everybody's got, let's parameterize some curves. Oh yeah. So if we give that thing a shot, what are we after in this first problem? At what points does some curve given by R intersect the paraboloid given by the equation that's over there? And since we just did the quadratic surfaces section, we totally know that that thing is a paraboloid. In fact, it's an elliptic paraboloid, but we just need to know it's a paraboloid for now. So let's start trying to figure that out. If we want these things to be equal to each other, we want to figure out where they intersect, I should just start plugging in my values for x, y, and z. So the x component of my curve is 7t. The z component of my curve is 5t minus t squared. And the y component of my curve is 0. So notice that there's just a 0j that wasn't listed there. So what I want to do is just plug each of those in for x, y, and z. Meaning I've got z, which is 5t minus t squared, is equal to x squared, which is 7t, plus y squared, where y is just 0. Right, so to kind of connect some ideas going on here, I've got this equation is really the equation I'm using down here, but with each of the components from the curve plugged in. So I know if these two things are going to be intersecting each other, their equations should be equal. So I've turned this thing from a 3-variable problem, x, y, and z, into a 1-variable problem, just t. And since I've only got one equation, I ought to be able to find a value for t. So let's do that. The left side, if I simplify it, really didn't need any simplifying. It was already 5t minus t squared. I'm going to drop my parentheses because I don't really need them anymore. On the right side, I've got 7t squared, which is 49 times t squared, plus 0. Reorganize some of these thoughts, and I should get 50t squared minus 5t equals 0. I just chose to group things so that my t squared coefficient was positive. And then I should factor the right side as much as I can. I can pull a 5t out of both pieces, leaving me with 10t minus 1. And that creates two possible solutions for t from the zero product principle. Either I get t equals 0, or I get t equals 1 over 10. Right, because either one of those things will make the whole thing equal to 0. Remember, the zero product principle states that anytime I multiply two things together and get 0, then one of those two things itself must be 0. So what is it that we ultimately wanted to do? Wanted to find two things. We wanted to find the t values that work, which are 0 and 1/10. And we also want to figure out what those points are, which means taking t and plugging them into r. So I'm just going to rewrite what r is in a spot where I can see it from the bottom of the screen. So r of t was the vector 7t 0 and 5t minus t squared. Didn't exactly write that straight, did I? Oh well. It's an artistic choice. So I just need to plug 0 into r. So r of 0 gets me my first point. Conveniently enough, that's just 0, 0, 0. And then I also need to plug 1/10 in for t. And that'll give me the vector 7 over 10, 0, and 5 over 10 minus 1 over 100. Oh, but this is a point, not a vector, so I'll use parentheses. I suppose it could be a position vector, but we don't need to bother with that. We'll just call it a point. Cool, so 7 over 10, 0, and if I wanted to simplify that, 49 over 100, I think. 50 over 100 minus 1 over 100. Yeah, it's 49 over 100. Cool, so that one's not so bad. The one that I know everyone's going to have the most fun with, probably. One like this. Here's two quadratic surfaces. One is a cylinder and the other is a surface, because we just called it that. So we aren't going to bother trying to classify that other one. It's a little above our pay grade right now. But I believe it's a paraboloid of some kind. But I think it's even a hyperbolic paraboloid. But again, we don't need to worry about that right now. We're just calling it a surface. So we've got a cylinder. Notice this one's a cylinder with a circular base. So the regular kind of cylinder that we're used to. So let's parameterize this thing. And I'm going to go over a couple of different thoughts on parameterizing stuff. first thing I see here is that I have an x squared plus a y squared. So I've got two square terms added together, and it's equal to a constant number. Specifically, it's equal to 81. If I see two square terms added together equal to a constant number, that makes me think sine plus cosine is going to be a good parameterization for what I'm trying to do. So using some kind of a, polar parameterization, similar like what we would have done back in polar coordinates. That's my first thought. So I'm going to try something like that. If I were to have altered this problem just slightly, say I had x squared plus y squared equals 81z, then I'm thinking this is probably something else. Probably something else. And by something else, I mean not sine and cosine. Where the important element of this is that z on the other side. I have something that was non-constant that my two square terms are equal to. So this sine plus cosine parameterization really only works if I see the equation of a circle show up, or maybe an ellipse, but still. I need it to be equal to a constant number for the sine plus cosine parameterization, at least for now. But with that in mind, since I do have it equal to a constant number, I'm going to have x be my cosine value and y be my sine value. So I'm going to claim that x is 9 cosine t, and y is 9 sine t. Nice thing about the sine and cosine parameterization is that it takes care of two of my variables right away. Notice that I put a 9 on each of the sine and cosine because the radius of that circle is 9. Right? Square root of 81 is 9. So I've got a circle with a radius of 9. So I'm slapping a 9 in front of sine and cosine. And to get z, it ends up being nicely straightforward. Because I already have an equation for z. I know it's 2 times x times y, 2x, y. So that equation could be 2 times 9 cosine t times 9 sine t. And I'd be tempted to just leave it right there, because I can see where all my pieces are coming together. But if you wanted to FOIL all this out, you could. I think that's 162 sine t cosine t. I don't know why, but it feels right to write the sine first. Just rolls off the tongue better, I guess. Or if you wanted to get real fancy, this thing is 81 sine of 2t, since that's the double angle formula for sine. Again, if you've taken trigonometry at Michigan State, you've probably also heard me talk about that formula. But you probably didn't think that was coming back. And it kind of isn't, but just for fun. I think stopping right here is fine. That's where I'd leave it if it were me, probably. But since that problem wasn't hard enough, let's try something else. Let's try and parameterize a totally different problem. Here's one I made up. I've got a paraboloid and a parabolic cylinder. Rather than me just going right to the answer because I know what to do, let me talk about my process for how I might start trying to parameterize something and at what point I think I should bail on a bad parameterization. So I think that might be helpful to see. So I start off with this collection of letters and a couple numbers, and I'm supposed to try a parameterization. I look at my first term, or my first equation. I see two square terms added together, right? I see an x squared plus a z squared, but it's equal to y. Specifically, it's not equal to a constant number. So I don't think that a sine and cosine parameterization is good for this intersection. So if that's not going to work, probably I just want to pick one of my variables and let it be t. And we're just going to run through the alphabet. So let's try x equals t first. Purple for x. So if I do that, the easier equation to start with, I've got x equals z squared. That now becomes t equals z squared. So solve that equation for z, which at first glance, maybe you say it doesn't look that bad. It's only one term on each side. But it gives us the equation z equals plus or minus the square root of t. Right, since parabolas are not technically invertible, or at least they don't have an inverse function. They do have an inverse relation, but we usually like functions when we're parameterizing something. So that plus or minus that shows up, because we had to take the square root of a variable, that's not great. Yuck. Yuck. So let's try something else. Let's try something else. I'm apparently writing down as I narrate. So if that parameterization didn't come out great, maybe another parameterization will. Draw in a line right here to differentiate. I'm moving on to a different method. If x equals t didn't work, you don't have to be a psychic to think I'm going to try y equals t next. I've only got one equation that's got y in it, and that was the first one. T equals 13x squared plus 4z squared, and I don't even know where to start on that. That looks pretty bad. I still have two variables left over. I could start trying to replace them, like x is z squared, so I could have 13z to the fourth plus 4z squared equals t. But that also looks ugly. Also looks ugly. Hard pass. That was worse than the last one. So I don't want to do that. Meaning I should try another parameterization. And I should move that thing down so that I have space to try my other parameterization. I'll draw another line in right here. If x equals t and y equals t didn't work, then what about z equals t? What? No way! I can't believe we tried that next. I've been in this review too long. Okay. Trying z equals t. That's gonna give us the equation. X equals t squared. Hey, that's not too bad. X is already defined just by defining z. So that's cool. Don't need to do anything else. X is already isolated. So I should take that and plug stuff into the y equation. So y is equal to 13x squared. 13 starts with a 1. Good job, Steve. Cool. So 13x squared, but now I know that x is t squared. So x squared is t to the fourth. Plus, on the other side, I've got 4z squared, but z was just t. So this is 4t squared. And hey, just like that, y is also defined. So now I've got an equation for each of x, y, and z, and it was basically easy. So I'm going to write that in. So in the end, my parameterization, r of t, this thing is, where did we go? X is t squared, y is 13t to the fourth plus 4t squared, and z is t. And that's my handy dandy parameterization. At least the one that worked. All right, just a couple problems left. Okay, so what's next? We want to find some arc length. So here's a curve, calculate its arc length where t is between -1 and 4. So this one's just an integral problem. At least we don't have to think too hard about it. We just have to plug some stuff in and integrate. So I want the arc length formula, which is the integral from a to b of the magnitude of the r prime vector dt. So that's our t value and stuff up there. We are going to need r prime, aren't we? Let's go get that. R prime is the vector 2. Derivative 2t is 2. Derivative of sine 2t is 2 cosine 2t. Oh no, my pen decided to disconnect again. I guess it's also getting tired. It's okay, buddy. We're almost done. You can make it. Ooh. Oh, never mind. It's not my pen that died. It's my whole tablet. All right, hang on just a second. All right, and we're back. So I just took the derivative of the x component. So now let's take the derivative of the y component. I might have even said that before my tablet crashed. But I believe that derivative is 2 cosine of 2t. And then the derivative of the z component, -2 sine of 2t, since the derivative of cosine is negative sine. All right, we've got ourselves an r prime vector. Let's go plug it in. Plug it in to our arc length formula. So I want the integral of the magnitude of r prime. The magnitude is going to be some square root. I'm not going to put the hat on it yet because I don't know how long it's going to be. I need 2 squared plus 2 cosine 2t squared. 2 cosine 2t. All of that squared plus -2 sine 2t. All of that squared. This square root needs a hat and maybe also a taller radical. And a straighter hat might also be helpful. Don't forget your dt. It should be there. Just tells us what our integrating variable ought to be. It's particularly important when we've got too many variables. And a and b. We're integrating from -1 to 4. All right. Let's fill the rest of this out. And also for consistency's sake, that should have been in black. All right. So what is this? What does this integral look like? It's pretty scary right now, but I'm hoping by the end it won't be so scary. So square all this stuff out. This is 4 plus 4 cosine squared of 2t plus 4 sine squared of 2t. Put my hat on my square root, throw a dt in at the end. Said throw it. Throw a dt in at the end, and then notice the holiest of the holy trigonometric identities. We've got a sine squared plus a cosine squared going on. So don't forget our Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1. You just have to make sure that the same angle is being plugged into both sine and cosine. But we have that. Our angle is 2t for both sine squared and cosine squared, which means that that entire inside of the square root is going to simplify ever so nicely to a number. So this is the square root of 4 plus 4 times 1 dt. And we're integrating from -1 to 4. And now that square root is just a number, which means we're really only integrating dt. And the integral of dt is t. So this is t times the square root of 8 being evaluated from -1 to 4. So that's 5 square root 8. And if you really wanted to, you could call it 10 root 2. Since 8's got a square number that we could pull out. But, probably at that point you're going to a calculator anyway, so step's not super necessary. But I guess I'm flexing my algebra muscles a little bit. Okay, one last topic, and then I'll get into some other bonus questions. Because this review wasn't long enough, so I decided to add some bonus questions. So cylindrical and spherical coordinates. Let's just identify some surfaces, because I think that'll be fun. So for the following problems, we're going to assume that we only have positive values for r, or rather non-negative values for r, because we will allow 0 in. But we just want to classify what each of these surfaces all look like. So let's talk about how to do that. Because you can, if you get really good at this stuff, just identify the surfaces based on their polar equations or their cylindrical or spherical equations. But probably the easiest way to identify them is going to be to convert it back into rectangular coordinates and see what the equation looks like. So if I've got something like theta equals pi over 2, what do I want to do for that thing? This one, actually, I'm gonna take it all back. And say instead, we should think about it in terms of its polar equation. Simply because this is a unique case. So theta equals pi over 2. Right? So if we're thinking about, our angle theta going in the xy plane, theta points straight up the y-axis. And then that's all it does right there. So we can move anywhere we want in the z direction. We can move anywhere we like up and down the y-axis, which means we're looking at a plane for that point. But specifically, we're looking at a half plane because r is non-negative. This guy's a half plane. Normally, if we've got theta by itself, we're supposed to take the tangent of both sides. But trying to take the tangent of both sides is going to result in an undefined answer on the right, as we try to get tangent of pi over 2. But tangent of pi over 2 is 0. That's not so good. Or tangent of pi over 2 is undefined, excuse me. Tangent of 0 is 0. Tangent of pi over 2 is undefined. The tangent... Nope. I'm going off on a tangent. Oh God, I've been here too long. All right, focus. An actual way that we could convert that thing into rectangular coordinates that'll make sense. Let's just take the cosine of both sides. So if theta equals pi over 2, that means cosine theta equals cosine of pi over 2, and cosine of pi over 2 is 0. I could multiply both sides by r. So if cosine of theta equals 0, that also means r cosine theta equals 0, which in turn is x equals 0. That's the equation of a plane in 3 space. But again, only positive values for r, which is why it's a half plane instead of the full plane. Yeah. Okay. Let's look at another surface. R equals 2. This one's easy. We're in cylindrical coordinates, and we got r equals 2. That's a cylinder. The namesake of the coordinate system we're in. But just to make this thing look a little bit more like a cylinder, we could say that if r equals 2, I can square both sides to have r squared equals 4. And then that means x squared plus y squared equals 4. That's the equation of a cylinder from back in our parametric quadratic surfaces unit. So the next one, that one's going to be more fun. Z equals 4 minus 8r squared. But we might as well just convert that into z equals 4 minus 8x squared minus 8y squared. So we've got some kind of a parabolic shape. And both our square terms have the same sign, so it's elliptical. It's also nice that there's only one paraboloid option in the multiple choices, but we could also identify that as an elliptic shape. Elliptic paraboloid. Cool. So let's maybe write some equations that come up with other values. That might be thinking too hard. Let's take that and move on. Let's also investigate spherical coordinates, because we should do that too. So same set of choices, but now we're moving into the spherical coordinate system instead of the cylindrical one. So this time we've got a surface. Phi is equal to pi over 4. And this guy is, well, this guy's a cone. Let me start with an answer and then work my way back into something. If I want to argue that this surface is a cone, maybe I do something like taking the tangent of both sides. Phi is equal to pi over 4 means tangent phi equals tangent pi over 4. The tangent of phi, sine over cosine, that's going to be r over z equals tangent of pi over 4, which is 1. So I'm briefly converting to cylindrical coordinates because I think it'll be easier. So I've got the equation r equals z. Then I could square both sides. R squared is z squared, so x squared plus y squared equals z squared. So if you really like quadratic surfaces, here's that original equation rewritten into rectangular coordinates, and that's the equation of a cone. Alternatively, if we try to get a sense of what spherical coordinates look like, phi is just the angle being made with the z-axis. So we're free to spin around the xy plane as much as we like because we've got nothing defined in that xy plane. We're only defining the angle we make with the z-axis. And so if we're just picking some angle to have with the z-axis, then that thing's a cone. So anytime we get phi equals some angle, our answer's always going to be a cone, with one exception. It's the same one we talked about in the previous problem. If we got phi equals pi over 2, this thing would be like a flat cone, since our angle is 90 degrees, but a flat cone is a plane. Specifically, it's the xy plane. But if phi is equal to any other angle, we're gonna have a cone, as long as the angle is between 0 and pi, which is usually what we restrict ourselves to when we're talking about pi. 0 being the positive z-axis, and then pi getting us all the way down to the negative z-axis. All right, then next up, the surface rho, because we use rho instead of r in spherical coordinates, equals 2. Well, this is the namesake for the spherical coordinate system. It's a sphere. It's the easiest shape to represent in spherical coordinates. Just rho equals 2. It's a sphere with a radius of 2. But the way to get there, rho equals 2, square both sides. I said square both sides. Means rho squared equals 4, and then that's x squared plus y squared plus z squared equals 4. That's a sphere. And then the next one over is also a sphere, I think. Just an odd way of getting there. So let's talk about why it happens. So this is the one that I think is most useful to see its conversion into rectangular coordinates. So I've got rho equals 3 cosine theta sine phi. And we got to do something with this. Right? Right. Probably. Actually, is this thing going to work out to a sphere? Let me cross that out for a second. No, I'm not so convinced. If it were cosine phi sine theta I degree, or do I have that backwards? Nope. Nope. I've thought myself around too many circles. Let me just do the thing that I was going to do and hope that I was right the first time. All right, let's multiply both sides by rho. So notice this time I'm not squaring both sides, whereas previously I'd been doing that a lot when I had rho or r isolated. I said that a good first step would be to multiply both sides by rho. This time, I think not so much. This time I decided to multiply both sides by rho. Reason being, is that the other side is not just a constant number anymore. When it was rho equals 2 or r equals 2, squaring both sides is easy because I just get r squared equals 4. Easy enough to work with. I don't really want to square the other side of this equation because that looks ugly. The thing that I do want to do is attach a rho to both sides. I want to attach a rho to that sine phi cosine theta bit because I think that that'll be helpful to us. So doing that on both sides, I get rho squared. Still achieve the same goal on the left of getting rho squared, but on the right, I get 3 rho sine phi cosine theta. 3 rho sine phi cosine theta. You know what? I actually am going to write that all out in purple. Sine phi cosine theta. So if we think back to our definitions for what x, y, and z are in spherical coordinates, I think that z is rho times cosine phi, right? So it's just the z is just the adjacent part of the phi angle, and that's all it is. Then the sine part of our phi angle, the opposite side of our phi angle, is going to put us into the xy plane somewhere. Sine phi, getting us to that opposite side, gets us r, effectively, the r that we use in cylindrical coordinates, just the distance from the z-axis. And then if I get r cosine theta, that thing is x. So r sine phi cosine theta is just x. So that whole thing over there on the right, 3 rho sine phi cosine theta, is just 3x. And the left side is x squared plus y squared plus z squared. And it's equal to 3x. And it might not look it yet, but this thing is a sphere. S-P-H-E-R-E. And the way we do that is just by completing the square on both sides. This will be x squared minus 3x. I might as well do the whole thing. Leave myself a gap. Plus y squared plus z squared equals 0. But I'm going to need to add 3 over 2 squared right here in order to complete a square, and then add it to the other side as well, giving me x minus 3 over 2 squared plus y squared plus z squared, and it's equal to 9 over 4. Which now written another way, that does look like the equation of a sphere. Okay, cool. That takes us to the end of all the problems that I wanted to do out in a whole, completing the whole thing, right before your eyes. There's a few more where I just wanted to talk some concepts, and I did those out already because we're already a ways into this review. So let's just talk in general about some more problems, some stuff that I think conceptually might be worth running over real quick. So what do we have here? We're given some vector valued function r, and we're asked to find its unit tangent vector. Ultimately, that's the thing that we want to do. Skipping over a whole bunch of calculation. So I'll calculate, a derivative vector, then I'm going to plug 2 pi into that thing, and then get the magnitude of box number 2. So get the magnitude of the vector with 2 pi plugged in. If I want the unit tangent vector, I take any tangent vector and divide by its magnitude. Gives me a unit tangent vector. Yeah, so blue box divided by the green box. That's all I really wanted to say about that one, conceptually speaking. Looking at some other simple questions. If I've got some vector, a is 3i plus 13j minus 2k, and I want the projection of A onto I. Remember that I is just the unit basis vector in the x direction. That is a simple way, or that's not it, that is a non-simple way of just asking, what's the x component of your vector? So if we set it up to do projection of A onto I, it's just the x component. It's just 3. All we got to do there. After that, evaluating a cross product. So I believe you can evaluate a cross product. You'll get a number. If we're going to evaluate that cross product dotted with J, that means just pick out the Y component of the cross product and give that as your answer. That's just a trick that we use sometimes to shoehorn a question into a format that D2L will accept. So this isn't expected to be like an extra hard step for you to do. This is just a, make it something that's easy for D2L to understand. Some other things. Got a couple of planes. I want to find their line of intersection and the angle that's in between them. Well, I can get a normal vector of each plane, take the cross product of their 2 normal vectors, and that will give me a vector that is parallel to their line of intersection. So that's what I did. Gives me my parallel vector, which means I then just need to get a point that's on the line. I do that by just picking one of x, y, or z to be any number I want. I think it's usually easy to just pick one to be 0. Then you get a system of 2 equations with 2 unknowns, solve that out, and add it up. I don't get a very nice looking vector, but I do get an answer in the end. Then a big thing that shows up here, calculating the angle in between those 2 planes. Well, the angle in between the planes is the same as the angle that's in between the normal vectors, with one caveat here, the part that I wanted to save and write in myself, is that I want the absolute value of the numerator. So that I only come up with the acute angle that shows the intersection between the planes. If I don't put the absolute value in, I'll still get an answer. I'll just get the obtuse angle that's in between the planes, right? If you think 2 planes intersect with each other, there are 2 angles I could use to represent their intersection. One of them is smaller than 90 degrees. The other is larger than 90 degrees. Or maybe they're both 90 degrees if they're perpendicular to each other. But still, I know that we'll often ask for just the acute angle that's between them, which means I want the absolute value of the inside to ensure that I come out in the first quadrant. Past that, what else have we got? A couple other curves. We want to know where they intersect. So if I want 2 parametric curves with different parametric letters, if I want them to intersect, that means I just need to set them equal to each other. So what did I do here? I'm ultimately going to want their derivative vectors, but not right away. I want to start by just figuring out their points of intersection. So I'm going to set the x's, the y's, and the z's equal to each other. And then I'm just going to solve the easiest equation first. I thought z was the easiest equation, so I started there. That's where I get that s equals negative t minus 2. So starting with that, the magenta side, plug it into the next easiest equation, and then I can solve for one of my variables. I said y was the next easiest equation. I think x looks the hardest, so I'm going to save that for the end. So plug z into y. That'll get me a number for one of my variables. I can then take that number, plug it back into z to find the other variable. So I got 1 and negative 3 for t and s respectively. And then I can just plug those 2 numbers into x and verify that it worked. Because if y and z are equal, And then I can also verify x is equal. I must have found a point of intersection. So plugged it in and say, okay, cool. I get that everything works out. These things intersect at the point -2, 1, 9. Because I can also verify by plugging t and s into their respective equations to see that I get the same point. Then I wanted the angle between the two curves where they intersect. That's where the derivative vectors come into play. So I need r prime, r1 prime, and r2 prime. And then I'll look at the magnitude of those two things together. It also looks like I got lazy and stopped writing all the primes in. That's not very good. These are all supposed to be primes here, and here, and here, and here, and here, and here. But this is just the formula from dot product, because that's the easiest way to get to an angle between two vectors. And finally, I had one more thing where I needed to look at a trick that might come up in integrating an arc length. So trying to integrate some square root. A u substitution can work if you really need to, but it might help if you simplify it a little bit first. I had a t squared that I could pull out of everything, meaning a t can come outside of the square root, making this a much easier integral to handle. So the trick, the whole reason I put this problem on here at all was showing off taking this t squared out of the inside of a square root so that I had an integratable function. Because we're not going to throw, the hardest integral at you on these exams. There's enough extra stuff to be quizzing you on. All right, and that takes me to the actual end. So hopefully you found something useful in this super duper fun review that definitely was as short as I expected it was going to be. If you've now watched this video and you have any other questions on what went on in here, feel free to make some posts on Piazza about it. I'll be active there and can come answer your questions. And other than that, good luck on the exam. Don't forget it's Thursday from 7 to 9. Feel like a commercial announcer. Get me out.